Hey guys, it's Mr. Calderon with Queen My Pawn. Today I'll be discussing the bits and bytes of binary. Where exactly is binary used? Well, every time you're using a computer, binary is being used. In fact, computers only understand binary. Whenever you see a number like 300 on the computer, it's actually written in binary. So it's a series of 0 and 1s. That's what binary means. The bi means two. Like bicycle has two wheels, binary has only two digits, a 0 and a 1. So I'm going to begin sharing my screen so I can exactly show you what is going on when we talk about binary. So let's say that I have something like the number 6. Well, if we only have zeros and ones, how are we going to exactly get 6? Well, let's start by counting. If I have 0, well, simply just 0. If I have 1, then simply just 1. But now 2, well, I can't represent 2 because as you can see, that's 3 numbers. But 2 can be represented as 1, 0. And then 3 can be represented as 1, 1. And then 4 can be represented as 1, 0, 0, and so on. So you can see actually that every space is a power of 2. So 4, for example, is 2 to the power of 2. If we skip a couple of numbers to get to 8, it'll actually be 1, 0, 0, 0. Here's how it works. The first digit is 2 to the 0. The second digit is 2 to the first. The third digit is 2 to the second. And the fourth digit is 2 to the third. Now, before you get lost, because that's probably what you actually are right now, binary is similar to decimal. Decimal actually means 10 or 10th in Latin. So let's consider the number in decimal, like 573, right? Well, we learned in elementary that this is just 500 plus 70 plus 3. But actually, look at this. This is 5 times 10 to the second power. And then that's right here is 7 times 10 to the first power. And then here, that's 3 times, let me write that 3 again, 3 times 10 to the 0 power. In binary, it's the exact same thing. If we have 1,000, this is what we're doing. 1 times 2 to the third power is 8. And then 0 times 4 is 0. 0 times 2 is 0. 0 times 1 is 0. So you add all that up and you get 8. That's exactly what's going on. So let's do an example. In blue, let me go over here and let's do one in blue, like 1, 0, 1, 0, 1. Well, I know that I have this on 2 to the 4, and then 2 to the second, and then 2 to the 0. Well, this is how I start counting. I start counting from the right. So I know this is right here a power of 0, 2 to the power of 0, which is just 1, by the way. Anything to the power of 0 is 1. And then here, 2 to the first power, which is just 0. 2 to the second power, that's 0. And then 2 to the fourth power. So I add all of them up, okay? I add these up. I'm going to get 8 plus 4 plus 1. So 1, 0, 1, 0, 1 is 13. And you can always verify that by going in Google, 1, 0, 1, 0, 1 in binary. And you're going to get 13. Well, you can ignore that because it thinks that I'm putting in 10,101. But let's see, maybe get calculator works. It says 10,000 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101. 101 Oh, I did my math wrong. It's not 13. 2 to the 4th power is 16, so I made a mistake. So it's 16 plus 4 plus 1, which is 21. That's a mistake for sure. And that's why we get 21 here, not 13. 13 would have been something else. But that's basically the gist of it, okay? That's just 16 plus 0 plus 4 plus 0 plus 1, and so on. And you can do different examples on your own, but why are we even using binary? Like where did binary come from so that we use it on computers? Well, the reason why we're using binary is because we have these things that computers use in their hardware, and they're called transistors. They're a piece of hardware, and it has basically a gate where electricity travels through. And you can either give it electricity or not give it electricity. So just like binary, it's yes or no, 1 or 0. So it's 2 choices. So that's why it works. And that's basically why we use binary in our computers. But binary is also represented as bits and bytes. So one of the reasons why we call them bits and bytes is, well, let's start off with a bit. A bit is called a binary digit. So for example, this right here is 1 digit, that's a bit. Here's another bit, that's another bit, and that's another bit. Now, when you have a bit, you know, when you say like something like a little bit, it literally is like just a little bit. But let's say you have a byte of something, then you have a lot of it. You know, like if I have a sandwich and I take a bite of it, I'm not taking like a little bit, I'm taking a bite. So a byte is 8 bits, okay? Now, originally it was spelled like this, byte as in B-I-T-E. I'm gonna put it bigger. So the creator of this, and I'll get to that in a moment, the creator of this realized, oh, this is a misspelling of, we should misspell this so that we don't get it confused with the actual byting. So they put B-Y-T-E. So a byte is 8 bits, which means that you're gonna have 8 spaces. And why did we create the byte? Well, here's why. There was a man named Werner Buchholz, and he was working on a computer in IBM. And one of the addresses, like one of the instructions had a size of 8 bits like this. And then he thought, oh, that's a byte of something. So that's where it actually comes from. So you can thank Mr. Buchholz for that. Now, another reason why we use binary is because like the transistors, the reason why we use it even in transistors is that the first person to notice that was Claude Shannon. And Claude Shannon used George Boole's paper on his algebra, Boolean algebra, which dealt with either yes or no. And then Claude Shannon noticed that that was similar to an electric circuit. So then he applied that into computers, and thanks to his thesis, we have binary in computers. So like Newton said, he stands on the shoulders of giants. Well, this is a clear example of it. Now, what's the biggest value that a byte could have? Well, since you could either put either 0 or 1 in all of them, well, the biggest value has to be 1, 1, 1, 1, 1, 1, 1, 1, which is going to be 2 to the 0, plus 2 to the first, plus 2 to the second, and so on. 3, 4, 5, 6, 7, right? You're adding all that up. And when you add all of that up, you're gonna get 255. So basically, you could have this as the biggest value of a byte. So bytes range in value from 0 to 255. I'm gonna write it as a hyphen. But what if we want to represent negative numbers? We got a problem because this can only fit positive numbers. But now we can accommodate by using the first bit as the sign. So we're gonna write 0 for a positive number and 1 for a negative number. So for example, let's put 1 as, because to signify it's a negative number, and then let's add zeros to the rest. All right, so since now we have to shift everything so that this is the biggest positive number. Well, this right here, it's just 2 to the 6 plus 2 to the 5, etc. The biggest now number is 127. And that means that you're gonna have numbers that range from negative 127 to 127. So that's the new range. Instead of 0 to 255, you now have negative 127 to 127. Now, basically, this is called the ones complement. So as you can see, this right here would be the opposite of this. It's called the bitwise not operation. We turn everything into the opposite to get this. So I'm going to show you a table right here. And let's zoom in. So as you can see, this table right here on the right, you can see that this number is negative 127. And this number, the opposite, the bitwise not, is 127. But we got a problem. The problem is this, is that when you put in all ones, you're gonna get negative 0 because you just basically count all the way down, right? We're counting. You can see that at the start, you get negative 127, and then you add 1, and then you get negative 126, and so on. You count all the way down, you get to negative 0. But that's a problem because we already have a 0, and there's no such thing as negative 0. 0 doesn't have a sign. So this is a problem when it comes to binary addition. But now binary addition is super easy, okay? It's just like regular addition. 0 plus 0 is 0. 1 plus 1 is 2, but remember that there's only 0 and 1. So you would get 0 and carry over the 1. So over here you have 1 plus 0 is 1, but you added the 1 because you carried it over. Now you get 2. But again, there's only between 0 and 1. So you carry that over, make it a 0, and then you have 1 plus 0 is 1, but then you carry over the 1, and basically you repeat the process so you get to the end. You're going to find out that you get this, which means you went over, and then you don't get a correct answer. So you had to carry over this 1, and then you end up with the correct answer. But this is complicated. This is not what we want. So the 2's complement was created. It's basically the same thing as the 1's complement, except now we just subtracted 1 more. So that way we just automatically carry the 1 over. And what's awesome about this is that now you end up with an extra number. Is that now instead of negative 127 to 127, you now have negative 128 to 127. And that's amazing. We just created a number just by shifting everything to the left. by 1. And the reason why that works is because from -1 to -128, there are 128 numbers. And from 0 to 127, there are 128 numbers. So you end up with 256 numbers. Just like over here, you have 256 numbers. 0 to 255, that's 256 numbers. Then -128, oops, to 127, that's 256 numbers. So it all works, it all corresponds. So it's perfect. Great. Now I was gonna go over how to do binary subtraction, multiplication, and division. And I'm not gonna lie to you, binary subtraction is a little bit hard to understand at first. But the good news is you don't have to know it for now. Multiplication is super easy and division is super easy. You just have to know subtraction. And I think I've covered everything I would needed to cover. Oh, no, I haven't. So let's think about what a size of an integer is in Python, like the number 5. Well, 5 only takes up this amount. If you put 5 in binary, you're just gonna get, let's see. This is how you find out a number in binary, 5. Okay, well, what's the power of 2 that's close to 5? 4. So 5 minus 2 to the second power. That'll give you 1. Okay, great. So then 1 is just the power of 2 to the 0. 1, and then 1, it's minus 2 to the power of 0, which is just 0. Once you get 0, you're done. So the answer is 101. Another example is, let's actually do 13, right? 13. Well, a power of 2 that's close to this is 2 to the third. So 13 minus 8, because 2 to the power of 3 is 8. 13 minus 8 is 5. And then 5 minus 2 to the power of 2 is 1. So you just get these. 8 plus 4 plus 1 is 13. So the answer is 1, 1, 0, 1. 8, 4, 2, 1. 8 plus 4 plus 1 is 13. So it works. And that's how you do binary. Anyways, so that means that it should only be 1 byte, right? Well, let's see. So I'm going to do import sys, because sys is a module, which is basically a collection of functions Python has. And it's going to tell me the size of an integer if I pass it in. And it's going to say 28. And what gives? That's really, really big. 28 bytes? That is huge. That's an enormous amount of data. Like, that can't be right? But actually, here's the thing. Everything in Python is an object. So an object has attributes, and attributes are things like the name, the size of itself, where is it located. All those things take up space. So the address takes up space, the size takes up space, and it has another field, which is the type of the variable, which takes up space. So you have the type, an integer. You have the size, which is self-determined. And then you have the reference count, exactly. So how many times it occurs in the code. All these things take up space, and what you're going to end up with is those 3 things take up 8 bytes each. So you're going to get 24. So the actual amount of bytes that the integer has is 4 bytes, which is 32 bits, which means that 32 bits would be 32 spaces. So basically, you have 1 bit for the sign, of course, and then the other 31. Well, it turns out to be 30. And I'll get to that in a moment. So you have 30 spaces. So the biggest number should be 2 to the power of 30 minus 1. Let's test that out. Okay, sys gets size of 2 to the power of 30, which is written like that. It's still 28, right? Now watch what happens when I take away the minus 1. You see how it goes to 32? Because we went over. And now I need an extra 4 bytes. So now watch what happens when I get to 60 minus 1, which is basically I'm still in like 2 to the power of 59, sort of. It's like 59 times, okay? 32, right? But now I go to 2 to the power of 60, and that's 36, and I need another 4 bytes for my next digits. So we have that killer overhead. Now there is NumPy, and I am not an expert at NumPy, but I can tell you that it's another library just like sys is, and it's able to have integers without all that overhead. Okay, so it's got its own objects without all that overhead, and so it'll make your program a lot smaller. Now, the reason why we have 30 is because let's say you have a 16-bit system. Well, then, or 16, hold on. Yeah, it's 16 bits. Let's say you have a 16-bit system. Then you need 1 sign for the, you need 1 bit for the sign and 15 bits for the digits. Now multiply that by 2, and you're gonna get, you would get 2 digits right here, 2 spaces for the sign, and then 30 for the actual digits. But obviously this is redundant, so we just use 1 sign, and basically the other space is it's lost. So that's where that comes from. But I've explained so much in this video for you to digest, and I think that's definitely enough. So I hope you enjoyed this video. Make sure to give it a like if you liked it. Comment if you have any questions, which you probably do. And subscribe, which is the red button, and I'll see you on the next one.